In this video, we will talk about the most common types of hard disks in a databases. We're going to explain disk geometry and other partitioning concepts, how disk devices are named, and how to identify their associated device nodes, how to distinguish among and select different partitioning strategies. We're going to discuss how to use utilities such as fdisk, blkit, and lsblk, backup and restore partition tables. Common disk types. There are a number of different hard disk types, each of which is characterized by the type of data bus they are attached to and other factors such as speed, capacity, how well multiple drives work simultaneously, etc. Here are the different hard disk types, right? SATA, it's a Serial Advanced Technology Attachment. SATA disks were designed to replace the old IDE drives. They offer a smaller cable size, 7 pins, native hot swapping, and a faster and more efficient data transfer. They are seen as SCSI devices. SCSI disks range from a narrow 8-bit bus to a wide 16-bit bus, with a transfer rate from about 5 megabytes per second, narrow standard SCSI to about 160 MB per second, ultra-wide SCSI 3. SCSI has numerous versions such as fast, wide, and ultra-wide. SAS uses a newer point-to-point protocol, has a better performance than SATA disks, and is better suited for servers. USB, these include flash drives and floppies and are seen as SCSI devices. SSD solid-state drives. Modern SSD drives have come down in price, have no moving parts, use less power than drives with rotational media, and have a faster transfer rates. Internal SSDs are even installed with the same form factor and in the same enclosure as conventional drives. SSDs still cost a bit more, but price is decreasing. It is common to have both SSDs and rotational drives in the same machines, with frequently accessed and performance critical data transfers taking place on the SSDs. IDE and the EIDE, these are obsolete. Disk geometry. Rotation disks are composed of one or more platters, and each platter is read by one or more heads. Heads read a circular track off a platter as the disk spins. Circular tracks are divided into data blocks called sectors. Historically, disks were manufactured with sectors of 512 bytes. 4 kilobytes is now most common by far. Larger sector sizes can lead to faster transfer speeds. Linux still uses a logical sector size of 512 bytes for backward compatibility, but this is simply for pretend in software. Cylinder is a group which consists of the same track on all platters. The physical structural image has become less and less relevant as internal electronics on the drive actually obscure much of it. Furthermore, SSDs have no moving parts or anything like the above ingredients, and for SSDs, this geometry concepts make no sense. Let's see the geometry with fdisk. Sudo fdisk -l v sda. You can see the geometry with fdisk here. The use of the -l option, this simplify lists the partition table without entering interactive mode. Partition organization. Disks are divided into partitions. A partition is a physically continuous region on the disk. On the most common architectures, there are two partitioning schemes in use: MBR, Master Boot Record, GPT, GUID partition table, right? MBR dates back to the early days of MS-DOS. When using MBR, a disk may have up to 4 primary partitions. One of the primary partitions can be designated as an extended partition, which can be subdivided further into logical partitions with 15 partitions possible. When using the MBR scheme, if we have a SCSI, for example, dev-SDA, then dev-SDA1 is the first primary partition, and the dev-SDA2 is the second primary partition. If we created an extended partition, dev-SDA-SDA3, it could be divided into logical partitions. All partitions greater than 4 are logical partitions, meaning contained within an extended partition. There can only be one extended partition, but it can be divided into numerous logical partitions. GPT is on all modern systems and is based on UEFI, Unified Extensible Firmware Interface. By default, it may have up to 128 primary partitions. When using the GPT scheme, there is no need for extended partitions. Partitions can be up to 2 to the power of 33 TB in size. With MBR, the limit is just 2 terabyte. Why partition? There are multiple reasons as to why it makes sense to divide your system data into multiple partitions, including separation of user and application data from operating system files, sharing between operating systems and or machines, security enhancement by imposing different quotas and permissions for different system parts, size concerns, keeping variable and volatile storage isolated from stable, performance enhancement of putting most frequently used data on faster storage media. Swap space can be isolated from data and also used for hibernation storage, right? Deciding what to partition and how to separate your partitions is cause for thought. The reasons to have distinct partitions include increased granularity of security, quota, settings, or size restrictions. You could have distinct partitions to allow for data protection. A common partition layout contains a boot partition, a partition for the root file system slash, a swap partition, and a partition for the slash home directory tree. Keep in mind that it is more difficult to resize a partition after the fact than during install creation time. Plan accordingly. MBR partition table. The disk partition table is contained within the disk's master boot record, MBR, and is the 64 bytes following the 446 byte boot record. One partition on a disk may be marked active. When the system boots, that partition is where the MBR looks for items to load. Remember that there can be only one extended partition, but that partition may contain a number of logical partitions. The structure of the MBR is defined by an operating system independent convention. The first 446 bytes are reserved for the program code. They typically hold part of a bootloader program. The next 64 bytes provide a space for a partition table of up to 4 entries. The operating system needs this table for handling the hard disk. On Linux systems, the beginning and ending address in CHS is ignored. Note for the curious, there are 2 more bytes at the end of the MBR known as the magic number, signature word, or end of the sector marker, which always have the value of 0x55AA. So each entry in the partition table is 16 bytes long, and it describes one of the 4 possible primary partitions. The information for each is active bit, beginning address in cylinder head sectors CHS format, partition type code indicating XFS, LVM, NTFS, ext4, swap, etc. ending address in CHS, start sector, counting linearly from 0, number of sectors in partition. Linux only uses the last two fields for addressing using the linear block addressing LBA method, right? GPT partition table. Modern hardware comes with a GPT support. MBR support will gradually fade away. The protected MBR is for backwards compatibility, so UEFI systems can be booted the old way. There are two copies of the GPT header at the beginning and at the end of the disk, describing metadata, list of usable blocks on disk, number of partitions, size of partition entries. Each partition entry has a minimum size of 128 bytes. GPT disk partition table. The BLKID utility shows information about partitions. On a modern UEFI GPT system, right? Let's take a look at it. We do sudo BLKID def SDA1. You can see that on this is on the modern UEFI GPT system, right? You can also see something on the MBR system, sudo blkid sdb1, right? See the different, right? Now, both examples give a unique UUID, which describes the file system on partition, not a partition itself. It changes if the file system is reformatted. The GPT partition also gives a part UUID, which describes the partition and stays the same even if the file system is reformatted. If the hardware supports it, it is possible to migrate an NBR system to GPT, but it is not hard to break the machine while doing so. Thus, usually the benefits are not worth the risk. Next, naming disk devices and the device nodes. The Linux kernel interacts at a low level with disks through device nodes, normally found in the dev directory. Normally, device nodes are accessed only through the infrastructure of the kernel's virtual file system. Raw access through the device's node is an extremely efficient way to destroy a file system. For an example of a proper raw access, you can format a partition as in this. You can format a partition by doing this, sudo memkfs.ext, or let's say, dev sdb1. I'm not really want to format it, so I'm gonna answer no. Right, device nodes for SCSI and SATA disks follow a simple XYZ naming convention, where XX is the device type, usually SD, Y is the letter for the drive number, A, B, C, etc. And Z is the partition number. Let's say the first hard disk is DEV SDA. The second hard disk is DEV SDB, right? So partitions are also easily enumerated, as in dev SDB1 is the first partition on the second disk. Dev SDC4 is the fourth partition on the third disk, right? So SD means SCSI or SATA disk. Back in the days where IDE disks could be found, they would have been dev HDA3, dev HDB, etc. By doing ls-l dev will show you the current available disk device nodes. BLKID. BLKID is a utility to locate block devices and report on their attributes. It works with the LIB-BLKID library. It can take as an argument a particular device or list of devices. Let's take a look at it. Sudo blkid dev sda this shows a use of a BLK with arguments, right? So you can determine the type of a content, example, file system swap, a block device holds, and also attributes, tokens, name equal value pairs from a content metadata, example label or UUID field. BLKID will only work on devices which contain data that is a fingerprintable. Example, an empty partition will not generate a block identifying UUID. BLKID has two main forms of operation, either searching for a device with a specific name equal value pair or displaying name equal value pairs for one or more devices. Without arguments, it will report on all devices. There are quite a few options designating how to specify devices and what attributes to report on. Let's dig more. Sudo blkid and sudo blkid-l root. All right. Okay, next. LSBLK. A related utility is LSBLK, which presents block device information in a tree format. As in this example, let me show you. LSBLK, right? And see, let's do LSBLK-H. This shows you the how to use it, right? The usage, LSBLK options, device, etc., right? Sizing up partitions. Most Linux systems should use a minimum of 2 partitions, root and swap. Root partition is used for the file system. Most installations will have more than one file system on more than one partition, which are joined together at a mount point. It is difficult with most file system types to resize the root partition, but using LVM can make this easier. Well, it is certainly possible to run Linux with just the root partition. Most systems use more partitions to allow for easier backups, more efficient use of disk drives, and better security. Swap is used as an extension of a physical memory. The usual recommendation is the swap size should be equal to physical memory in size, sometimes twice that is recommended. However, the correct choice depends on the related issues of the system, user scenarios, as well as hardware capabilities. Adding more and more swap will not necessarily help because at a certain point, it becomes useless. One will need to either add more memory or re-evaluate the system setup. Some distributions, such as Ubuntu, default to swap file rather than a partition. Well, this approach is more flexible. It is also more dangerous if error or bug occurs. Backing up and restoring partition tables. For MBR systems, DD can be used for converting and copying files. However, be careful using DD. A simple typing error or misused option could destroy your entire disk. All right, let me show you a command to back up the MBR along with the partition table. Let's do ddf equal dev sdb of equal mbr backup vs equal 512 count equal 1. Okay, the mbr can be restored using this command sudo ddf equal mbr backup of equal dev sdb vs equal 512 count equal 1. Right. So the dd commands only copy the primary partition table. They do not deal with any partition tables stored in the other partitions, for extended partitions, etc. For GPT systems, it is best to use the sgdisk tool. Let's do sudo sgdisk-p dev sdb, right? And if run on a pure MBR system, we do sudo sgdisk-p dev sdb, right? Partition table editors. There are a number of utilities which can be used to manage partition tables. Fdisk. Fdisk is a manual-driven partition table editor. It is the most standard and one of the most flexible of the partition table editors. As with any other partition table editor, make sure that you either write down the current partition table settings or make a copy of the current settings before making changes. sfdisk. sfdisk is a non-interactive Linux-based partition editor program, making it useful for scripting using the sfdisk tool with care. Parted. Parted is a GNU partition manipulation program. It can create, remove, resize, and move partitions, including certain file systems. The GUI interface to the parted command is gparted. Gparted is a widely used graphical interface to parted. Gdisk. Gdisk is used for GPT systems, but can also operate on MBR systems. Sgdisk. Sgdisk is a script or command line interface. Many Linux distributions have a live installation version, which can be run off either a CD-ROM or USB stick. This media usually include a copy of a gparted, so they can easily be used as a graphical partitioning tool on disks, which are not actually being used while the partitioning program is run. Using fdisk. Fdisk will always be included in any Linux installation, so it is a good idea to learn how to use it. You must be root to run fdisk. It can be somewhat complex to handle, and caution is advised. The fdisk interface is simple and the text manual driven. After starting on a particular disk, let's take a look at it. Sudo fdisk dev sdb. We type in M for help. Display this manual. All right, you can see for P, it's print a partition table. For N, it's add a new partition. For D, it's delete a partition, right? For T, change a partition type, right? For W, it's write table to disk and exit. For Q, it's quit without saving changes, right? So unfortunately, no actual changes are made until you write the partition table to the disk by entering W. It is therefore important to verify your partition table is correct with P before writing the disk with W. Let's do that. P, right? You verify it first before you write it back to the partition table. So if something is wrong, you can jump out safely with the Q, right? So the system will not use the new partition table until you reboot. However, you can use this command to bypass that. With Q, first of all, we can use this command to bypass that. As you sudo part probe -s. Right. To try and read in a revised partition table. However, this doesn't always work reliably, and it is best to reboot before doing things like formatting new partitions, etc., as mixing up partitions can be catastrophic. At any time, you can do cat proc partitions, right? You can do this to examine what partitions the operating system is currently aware of. Okay, this is the end of this video. Thank you for watching. I'll see you in the next one. Bye for now.